Hi everyone, we are Jan.
Paul Bard.
Julien Roy.
Today, we'll present our recent work on imitation learning without policy optimization. Let us start with background and motivation. In reinforcement learning, we consider a sequential decision-making problem where an agent takes an action and measures a state and a reward from the environment. Such an interaction between the agent and the environment is modeled by a Markov decision process and a policy. In reinforcement learning, our objective is to find out a policy that maximizes some rewards. In imitation learning, we consider a Markov decision process without a reward function. Instead of a reward function, we assume there is an expert demonstration. Our goal in imitation learning is to learn a policy that mimics experts' behavior from the demonstration. Conventionally, there are two ways for imitation learning. The first way is to match the trajectory distributions. The second way, which is a bit widely used recently, is to match the state action visitation distributions. Generative Adversarial Imitation Learning, or GAIL, applies GAN framework to the imitation learning problem. The objective of GAN is to train a general distribution that approximates the data distribution. To do so, GAN framework introduces a discriminator to classify whether samples are coming from a data or a generator, and a general distribution is updated to fool the discriminator. Similarly, the objective of GAIL is to match the agents and the experts visitation distributions. GAIL uses a discriminator to classify if state action pairs are coming from the agent or the expert, and an agent visitation distribution is updated to reduce the difference. Practically, GAIL uses interactive updates described as follows. First, we sample rollout trajectories from the interaction between the agent and the environment. Then, we sample state action pairs from both agents rollouts and experts demonstration and train discriminator with binary classification loss. Finally, we update the policy by using reinforcement learning algorithm and a reward function defined by a discriminator. However, GAIL's performance highly depends on the reinforcement learning algorithm, which complexifies the whole learning procedure. In our work, we propose an imitation learning method that trains both policy and discriminator simultaneously. We use the structural discriminator defined by the policy, which will be explained by our next presenter, Paul.
To understand how we can bypass the reinforcement learning step, we have to go back to the GAN objective. From it, we can define the optimal discriminator, D star, that would maximize it for any given generator. Goodfellow et al. Showed in the original GAN paper that D star has the following analytical expression. We see that the optimal discriminator depends both on PD, the data distribution, and PG, the generated distribution. This means that when the GAN objective is optimized so that the discriminator model retrieves D star, the model must implicitly learn both the true and the generated data distribution, as well as be re-optimized for any change of the generator distribution. Instead of directly parameterizing the discriminator, subsequent work therefore proposed to parameterize a probabilistic model P tilde from which we can define the discriminator. In this work, we qualify such discriminator as structured and show that P tilde actually recovers the true data distribution for any generator. The use of a structured discriminator is the foundation behind ASAF. Regular discriminators are usually composed of a neural network and a sigmoid function. On the other hand, structured discriminators rely on learnable parameters that define a distribution. One can choose a categorical distribution, a Gaussian, or more complex distributions such as mixtures and normalizing flows. This parameterized distribution gets us P tilde of x that is used alongside PG, another such distribution, to compute the output of the structured discriminator. For imitation learning, we deal with trajectories tau and their probabilities on the different policies. We can explicit the probabilities and write them as the probability of starting in that initial state, The probability of taking the sequence of action that we took, given the states we were in and the policy we were using, and the probability of transitioning to these next states. Crucially, we see that the environment terms cancel out and that, in the imitation learning case, the structured discriminator is entirely defined by the policies. This can be modeled by any parametrizable distribution, such as categoricals or Gaussians. For the specific structure, we show in the paper that the optimal discriminator retrieves a policy pi tilde that matches the trajectory distribution of the expert. Moreover, using the learned policy as generator is optimal. Indeed, when the learned policy is used as generator, even the optimal discriminator outputs 1/2 for any trajectory, be it true or generated. This corresponds to a discriminator that is maximally confused by the generator. This is super important and desirable because it means that we can update the generator for free. No need to update the policy with reinforcement learning anymore.
The theory for ASAF builds on the assumption that the discriminator is trained all the way up to optimality. In practice, we cannot expect gradient-based optimizers to find the global optimum when parametrizing our policies with neural networks, and thus we must use iterative algorithm similar to Gale. The algorithm takes as input the dataset of expert trajectories and starts by randomly initializing the discriminator model. For a number of iterations, we collect trajectories using the current generator policy by interacting with the environment. We then update our structured discriminator by taking gradient steps to minimize the binary cross entropy loss. And finally, we simply set the new generator to be the one used by the discriminator. And this is where ASAF dramatically differs from Gale. Instead of optimizing the generator for several RL steps, we simply need to make a copy of pi tilde, which saves us from a lot of computation and implementation. One remaining limitation is the requirement to use full trajectories. Very long trajectories can make learning unstable, and it prevents us from using unordered datasets of expert transitions. To overcome these limitations, we introduce two hyperparameters that generalize ASAF to the transition case, a window size and a window stride. For example, ASAF as presented above considers the entire trajectory, which is equivalent to choosing a window size as large as the episode length. A smaller window size cuts the episode into sub-trajectories. We call such variations ASAF W. The window stride corresponds to the number of transitions between the beginning of two consecutive windows. In particular, picking a window stride smaller than the window size causes the sub-trajectories to overlap, which can be seen as a form of data augmentation. And finally, we call ASAF1 the extreme case where the window size equals 1, recovering a transition-wise algorithm. So first, we evaluate our methods against Gale, Arrow, and Squill on OpenAI's classic control suite and find that all algorithms generally perform well. The goal with this set of tasks was to confirm that all three variations of our approach, so ASAF, ASAF-W, and ASAF1, can reach expert performance. We then evaluate on the MuJoCo continuous control environment, which involve larger action spaces and more sophisticated dynamics. In this set of tasks, using full trajectories does not perform reliably well, and ASAF1 is preferred, probably due to the significantly longer episodes. We also note that while Squill often reach high level of performance very rapidly, it also shows signs of instabilities, which is a major drawback in imitation learning, as in real application cases, one does not have access to the true reward function to monitor performance, which limits the applicability of strategies such as early stopping. Finally, we test our methods in the discrete domain of Pomerman. In this task, that we call random tag, the agent must learn to navigate to and eliminate a random agent without eliminating itself in the process. A task that is surprisingly tricky as the random agent often avoids the traps set by the learner. Apart from behavioral cloning, which performs surprisingly well here, all three variations of our algorithm outperform the baselines in that setting. That's it for the overview of our work on imitation learning without policy optimization. Thank you very much for your time, and we invite you to check out the paper for all the details.